Hi everyone. Today we'll discuss about the system design for a stock exchange. Let's first go through the functional requirements. We should be able to handle multiple stockbrokers. It should provide low latency trading and high throughput. This we can achieve by either using the FIX protocol or the FIX adapted for streaming protocol, uh, which is specifically created for financial transactions. Then it should be reliable. Basically, the latency should be predictable. We should provide fairness of trade as in irrespective of who is connecting or what institute is connecting. Ordering should be correct. Ordering should be predictable. It should be deterministic, is what it means. Then it should also be durable, as an act orders should be persisted. Shouldn't be like, okay, after some time, say if a machine crashes, we can't say that the order is lost. So it should always be persisted, and the system should also be robust to bad clients, right? Now, moving on to the non-functional requirements. Let's assume there are around 5,000 stocks that are traded, around 50 brokers, maybe even 100 brokers if you want. And say there are 1 billion orders that can come in a day. And the peak ops per broker may be around 10,000. Let's see some of the use cases also that we need to cover, that the system needs to cover rather. There should be multiple orders for the same stock at different price points that has to be handled. Then multiple buy and sell order for the same stock from a user needs to be checked. Possibly they're trying to manipulate the value. And then buy and sell orders for the same stock from users of the same trading company must be validated to make sure that the retail users are also provided fairness. And then sudden spike in orders for a single stock based on how the market behaves should also be handled. Considering the trading period as 9:30 a.m. to 3:30 p.m., there are around 6 hours. So the average operations per second will be around 50,000. Considering that there are 10,000 is the peak ops per broker and there are 50 brokers, there will be around 500K ops at the peak moment, peak time. So we should be able to support 500K. This I think we can achieve with the fast protocol that we spoke about earlier, and a lot of caching. Then 100 bytes per stock data. Let's assume there are 100 bytes of data for each stock that is traded. So the network capacity at peak might be 100 into say 500K, that is 50 MBs per second, which is actually okay. Now moving on to the system design. So from the brokers, the request will come to the API gateway, and the API gateway will forward the request to a scheduler. A scheduler is basically a system which keeps track of when the order needs to be triggered based on what is the trigger point and if it is a normal order or a limit order. So it keeps track of the pricing point and then ensures that the order is scheduled at the right time or triggered at the right time. And we'll have two separate queues. One is a buy queue and a sell queue. It will be at a per stock level. So the Apple stock will have a separate queue and the Google stock will have a separate queue in the buy queue and a sell queue. Now, the orders from the buy queue and the sell queue will be sent or taken by the sequencer. The sequencer is basically ensuring that the orders are sequenced in the right order to the matching engine so that the behavior of the matching engine is deterministic. Matching engine is nothing but a state machine where based on the ordered set of inputs, the output is always deterministic. So irrespective of how many times the orders are sent in that order to a matching engine, the output is always as expected, or it will be deterministic. Now we'll have three matching engines to which the sequencer will send the data at the exact same time. We can either use a UDP here or the fix or fast protocol itself. UDP should be okay, but if we use a UDP, then we need to have a separate, say, retransmitter service, which which will actually retransmit a packet if it is lost and if the matching engine is requesting for it. So we could multicast that to all the matching engines. Now the matching engine, uh, since since we are using three matching engines, the even if one of the matching engine goes down, which it can always come back up and see the sequence of messages that the other matching engine received from the sequencer, which would have actually cached. Let's say we use a Redis cache, which I have not drawn here, but the sequencer can have a Redis cache where it is actually keeping track of all the set of messages that it is sending out. Um, and the matching engine, if it goes down, it can request the sequencer for those messages. And since it is deterministic, based on the order of the messages, the matching engine will come back to the state that it was in earlier. And from then it can move on to the correct current position. Now the matching engine should also talk to a trade validator, which will basically ensure that there are no bad clients. Say someone is trying to manipulate the value, or if there are traders from the same trading company trying to buy and sell a particular stock to manipulate its value, all those checks can be validated using the trade validator. The job of the producer is to, once it gets the output from two out of three matching engines, it determines that that is the value for, or that is the status for a particular order. And based on that, the producer will send the data to a order management service, the analytics engine, and a trade reporter based on how the order went. Now, the order management service will send the response to the brokers to indicate the outcome of the order. And the analytics engine will take care of the analytics part for the system. And the trade reporter is basically, we have to indicate what are the trades happening and how they happened, and all the trade metadata that needs to be sent to whoever wants it. Now, in most part of this, we can use the fix or the fast protocol itself to achieve high throughput and low latency. But in some cases, we can also use, say, the UDP again to achieve low latency. But if we are using the UDP, we have to use a retransmitter service, which will ensure that the packets are retransmitted if they are dropped. Right. I think most of it is covered except that I haven't drawn the caching and the DBs. But since the matching engine is a state machine, we need to cache multiple things everywhere. And so that even if we replay the cached data, the state machine comes back to where it should be. One other point to cover here is that all the incoming messages that are sequenced will be recorded in the sequencer. The recorded data can be used for testing purposes of the, say, the system whenever it goes through a testing phase, right? Be helpful in that, and to validate the matching engine's performance, whether they are deterministic. Say if we have a new matching engine that has to be built, or changed, then the correctness of the matching engine can be checked by validating if the output is as expected, whether the output is deterministic. And that is one advantage that we have by recording the orders. I think most of it is covered. I'm not sure if I've missed something. If there is anything, please do let me know. I think we have covered all the aspects here as well. High throughput, low latency, multiple fairness, durability, robust. Yeah. Okay, that's all for today. Thanks, everyone.